Hey everyone, I'm going to do a probability review. I go over the notes that we kind of had through the course of this unit, and then I'm looking to do either a written test on Friday and Monday of this coming week, or maybe just do a fully online um, test on Monday, so that everybody kind of takes it at the same time, whether you're at home or in school. I'm doing it completely online through Edge Elastic um, to get it done and done before Christmas. Um, and then we'll come back after Christmas and start a new unit from there. So just remember, we're working on probability. Probability has two different types of calculations. There's a theoretical probability, which is the probability just looking at what we're trying to study. It's the probability that we would expect um, given the number of possible outcomes. So if I'm going to flip a coin, there are two possible outcomes, heads or tails. The theoretical probability of that is 50-50. There's a 50% chance you're going to get a head, or 50% chance you're going to get a tail. The empirical probability, that's what you're going to calculate as you actually do a simulation. So if you flipped a coin 10 times in a row and you got 7 heads, your empirical probability in that instance is 7 divided by 10, which is 70%. So you're kind of looking at it saying there's a 70% chance you're going to get a head if you flip a coin. That's going to change no matter how often you do a simulation. If you do multiple simulations, the empirical probability will more than likely be different for each and every one. It's just that we're still kind of basing everything on we expect the theoretical probability to happen. I mean, every time you flip the coin, you're expecting a head or a tail. It's a 50-50 proposition. But over a number of actual observations, the empirical probability is what you're observing as you go through the thing. So facts about probabilities, they're always between 0 and 1. You can't have a 2% or 200% probability of something happening. So they're always going to be between 0 and 1. They're always expressed as either a fraction, a decimal, or a percentage. You can see a 1 in 2 shot, a 1 in 6 chance of rolling a 1 when you roll a dice, a 50% chance of getting ahead on a flip a coin, or a 0.5% chance, or a 0.5 chance. So it's always a fraction. It's never going to be a whole. It can be a whole number. If you flip a two-headed coin, it's a 100% chance you're going to get ahead. If the probability of an event happening is 0, then that event never happens. So you never have to worry about it happening if the probability is 0. And if the probability of event happening is 1, then it's always going to happen. So you can always assume that's always going to be the case. You typically see 0 and 1 because there's always a slight probability that something will or won't happen. Another thing to remember too is that the event of something not happening. So the probability of getting ahead is 50%. Well, the probability of not getting ahead is just 1, where all probabilities are between 0 and 1. It's just 1 minus the probability of getting ahead, which is 50. So it's still 50% there. Think of rolling a dice. The probability of getting a 1 rolling a die is a 1 in 6 chance. The probability of not getting a 1 is just 5/6, which is just 1 minus 1/6. And then that non-event we always talk about, that's called a complement. When we see notation, we're going to see a lot of like P comma, parentheses A, P parentheses B stuff. The events are always represented with uppercase or lowercase letters. So if we talk about the event that it will snow tomorrow, that's going to be probability A. That A is the event, it'll snow tomorrow. If we're talking about it'll rain tomorrow, then that'll be event B. Event B would be that it will rain tomorrow. So when you see P and then A in parentheses, that means that we're talking about the probability of it will snow tomorrow. Usually you'll see kind of the A's and the B's identified even before you start talking about the probabilities on that. And just remember too that just because a probability is large, it doesn't mean the event is more certain to happen. Like a 98% probability of something happening, yeah, there's a highly likely chance it's going to happen, but again, it doesn't mean that it will. So our probability rules, rule 1 is probabilities are always going to be between 0 and 1, like we talked about. And then we said the probability the event will not occur is just 1 minus the probability that it will. I'm never going to use this A to the C thing, so just know that the probability of event not happening is just 1 minus the probability that it does. So finding theoretical probabilities is just as easy as looking at what makes up your possible outcome and divide it by the total possible outcomes. We're going to flip a coin. We're either going to get a head or a tail. So what makes up our outcome is just a head or a tail. the total likely outcomes are 2, it's heads or tails. So we always call these as well too. It's like we talk about equally likely outcomes. Like things have to kind of be equally likely, so there's a pretty good chance that anything's going to happen. So when you kind of start talking about what the theoretical probability is, just list all your equally likely outcomes, and then figure out what makes up your possible outcomes for that. Like if we look at an example of like rolling a dice, it's like we could talk about the possible outcome we're looking for is rolling a 1. So there's one possible outcome. There's one outcome we're looking for. That's our event, but we're looking at 6 possible outcomes. We could get a 1, a 2, a 3, a 4, a 5, or 6. Another thing we could be looking at, another event we could be looking at, would be rolling an even number. Well, now there are 3 possible outcomes, 2, a 4, or 6. There's still 6 total outcomes, so our chance of rolling an even number then becomes 3 over 6, or 1/2. So you say when they're equally likely, the probability that each event occurs is just the number of outcomes that makes up that event divided by the total number of likely outcomes. So it's really just a fraction. Like it ends up being, that's why we kind of talk about it as a fraction. So looking at our example, the probability rule number 3 then is the number of outcomes our event, A, divided by the total possible outcomes. So our example we used back at the beginning of this unit was a bowl has 10 dice in it, 5 red, 3 green, and 2 white. Probability of reaching into that bowl and picking a dice, there are 10 possible outcomes. We can pick up any one of 10 pieces of 10 dice. So there are 10 possible outcomes. But we're looking at the probability of picking up a red die. There are 5 red die, so the possible outcomes for that, the number of outcomes is 5 for A, picking a red dice. There are 5 red die in the thing. So our probability there is going to be 1 over 2, 5 over 10. There are 3 green dice, so there are 3 possible outcomes for our event there, 3 divided by 10, and then for the white die, it's 2 possible outcomes, so 2 divided by 10. So you got to kind of think of what are the possible outcomes for what I'm trying to do. So again, if we kind of think about rolling a dice, rolling 2 dice to get a 7, now we're looking at the number of possible outcomes of getting a 7. Well, we could either roll a 6 or a 1, but remember too, it's like we have 2 dice. Dice 1 could come up a 6, dice 2 could come up a 1, but we could also have dice 1 come up at 1 and dice 2 come up to 6. So there's 2 possible outcomes or 2 possible combinations of the 1 and the 6 adding up to 7. It's the same for the 2 and the 5, the same for the 3 and the 4. So there are actually 6 possible outcomes of rolling a 7 with rolling 2 dice. There are still 36 possible outcomes because the number of outcomes is just the number of outcomes on each dice multiplied together. So 6 times 6 is 36 possible outcomes. And then you have 6 over 36. So it's really just there's a 1 in 6 chance you're going to roll a 7 when you're rolling 2 dice. And that's kind of why we were doing the counters game when we were working on that, was everybody should have been putting most of their counters on 7. Yeah, there's some outliers where you're not going to always get a 7, but the best odds of getting an outcome when you're rolling 2 dice is getting a 7. Again, we're going to look at our data. We have our data tables. Now we're talking about like words with or and, where we're kind of changing what we're looking for. So we kind of look at some questions like, what is the probability of a randomly selected person being married? So when we have randomly selected people in the married column, we're just kind of looking at the probability of somebody being married. So we're looking at this, whoops, sorry about that. We're looking at the probability of being married. So we're looking at in this column. The probability of just randomly selecting a person to be married, it's just 408 divided by the total number of people, which is 665. That's the first one, is the 408 divided by 665. We can also talk about the probability, we're adding the word or now. So we're talking about the word or. So now it's what is the probability of a randomly selected person being married or having a college degree. So now we have 2 possible outcomes. The person can be married or the person can have a college degree. So now we kind of look at it, we're going to have the same 408 people. We can pick that satisfies our married people, 408. If we kind of look and say what's going to happen with the college degree, well, now we're out here. We're looking then at this 143 people, the 143 people with a college degree. So now we have we've satisfied both our conditions. People with married, people with a college degree. The thing you always have to remember, though, and we kind of talked about this before, is we're double counting these 98 people because they're both in our married column and they're both in our college educated row, so they get double counted. So the probability of picking somebody that's married or has a college degree, you got to back these 96 people out of the total number of people. So when you kind of do the math there, it's going to be 408 plus 143 minus 98, which works out to be about 453 people over the 665. Now we talked about the word or, because this is another thing. It's like changes what's happening. When we talk about or, now we're looking at having a college degree. I'm sorry, or is either or. Satisfies. And now means we have to find the person that's married and has a college degree. So now the people that we backed out of the or conversation, these 98 people, those are the people that satisfy our third question. So now we're just looking at 98 out of 665 people. Those are the 98 people that we can pick that are married and have a college degree. Does that make sense? So the thing kind of makes sense. You're gonna see a lot of these like table problems on the test or what we put together for the final thing as we go through it. Again, some more examples here. We're just using or. It's like, what is the probability of selecting a person that is single or married? So now you're just looking at the single column and the married column. There's nobody overlapping because you can't be single and married at the same time. So our total there is just 520 people out of the 665. Then we look at the second thing. It's the probability of seeking a person that is married or has a college degree. It's just like the one we just did. It's this 408 plus the 143 minus our 98 people that we double counted. So it's just like our last example. Okay, mutually exclusive events. We talked about this. It's two events have no outcome. There's no relation to their outcome whatsoever. So think of it, the mutually exclusive event. We're going to flip a coin and roll a dice. The events have nothing in common. So we kind of look at it as each of those can't happen at the same time. So like the last example, you can't be single and married at the same time. They're mutually exclusive. So probability rules for this now then, like we just talked about, is if the probability of or happens, an or event, it's the probability of our first event plus the probability of the second event minus the probability of them both happening at the same time. If it's mutually exclusive, and then it's just A plus B. Hope this is making sense. The conditional probabilities. This is where we're kind of talking about finding the probability given something to happen first. What's the probability of rolling a 3 given that we've already rolled the 1? Well, the only way we can find that probability is we have to roll the 1 first. The probability of rolling a 1 is 1/6. The probability then of rolling a 3 is again 1/6. So we're looking at a 1 in 36 chance of rolling a 1 then a 3. Does that make sense? Like we kind of look at the questions of what's the probability a Carver High School freshman is over 6 feet tall. This is the given that one. It's like we're looking at the freshman. We're just looking at Carver freshman. So given that it's a Carver freshman, what's the chance they're over 6 feet tall? The second one is the probability of a Carver High School student is a freshman and over 6 feet tall. Well, now we're looking at the whole student body rather than just the freshman class. That's the difference between those two questions. So typically you're going to see the conditional probabilities. It's the phrase given that. It's going to be given that somebody's married, what's the probability that they live in a house? Something like that. They can be a little bit more subtle where then you got to kind of figure out what they're talking about. I will try to stick with the given that statements on the test. Again, we're kind of looking at our data. Given that, it's like, what is the probability a college educated person is married? So it's not given that, but what they tell us is they're specifically stating a college educated person. So what we're looking at now is our pool of data is only 143 people. These are all the people that have a college degree. Now we want the married person, so we're looking at this box. We're looking at those 98 people are the married people with a college degree. Again, if we're looking at what's the probability of a person that is college educated, and married, again, it's still these 98 people because they have a college degree and they're married, but now this is out of the whole 665. Once you kind of get and in there, it's not a given, it's not a if-then statement. It's we're looking for that one specific event where people are married, people have a college education. The first one is college education first. We look for those people first. So we're limiting our pool of people to just college educated people. Like if I said, what's the probability of a widow or a widower selecting a widow or a widower given the person has less than a high school education? We're looking at these 28 people up here. We got to go to the less than high school education first. Then you go to the widows and the widowers. So again, when we talk about the given that in symbols, we kind of go, you'll see this vertical bar all the time in the symbols. That's the given that thing. So what is the probability a person is married given that the person has a college education? The second thing in the parentheses is the conditional statement we need to have satisfied first. So when you start seeing probabilities, it's A given B. This is what's the probability of A happening knowing that B's already occurred. Like I showed you, it's pretty easy to pull this stuff from the data table. If you just have probabilities of A's and B's and stuff happening, then the probability of A then B is just the probability of A and B, which have to be given. If we're just given the probabilities, divided by the probability of that first condition. So if we kind of look at our consensus, our data again here, and we kind of think about this formula, we're going to find the probability of A and B. So we're looking for, our example here is less than a high school degree and is married. So the probability is of having less than a high school degree and being married in our full data set is the 70 people out of the 665. So you'd have 70 divided by the 665. Sorry, I'm doing all this math with my mouse. So that's the probability of A and B happening. Again, like I said, it's divided by the probability of just B happening. And that's the probability of somebody being married. So that is now 408 divided by 665. So that's 408 divided by the 665. So then you do that math and you kind of find out that the probability of having at least a high school degree being married would be 70 divided by 408. Make sense? Independent events, those are the events that are going to happen no matter what happens first. So you flip ahead, it's independent of getting a tail. If they are independent events, in the given that statement, if they're independent, it's just the probability of getting A. So like if we look at our examples here, the probability of a card is a diamond, given that the card is red, well, that's not independent. The only way the card can be a diamond is the card has to be red. So their probabilities aren't going to be, it's not going to be the probability of A for that. Because you look at it, the probability of getting a diamond is 13 out of 52. The probability of getting a red card is 26 out of 52. So those probabilities aren't working out. Because when you do the math for it, the probability of the card's a diamond given is 1/4. But the probability of the card being red is 1/2. So it doesn't work out that way. Same thing with here. The probability of getting an ace is 4 out of 52. The probability of getting an ace, given that the card is a diamond now, is 1 out of 13. Sorry, probability of getting an ace is 1 out of 13. It's 4 out of 52. Probability of getting an ace is 1 out of 13 if we already know it's a diamond. So those are independent events. Sequence of events, we talked about that. This is where you got to multiply probabilities together to figure out what the probability of the two seeds of that sequence happening is. The more sequences, the more stuff you're going to multiply together, you can eventually find out what you're going to get. So our example was a boy and a girl. The probability of a boy being born first with a girl being next is the probability of the boy, the 51%, times the probability of the 49%. You just multiply those two together and off you go. Because it's still individual things. We want the boy to be born first. So there's a 51% chance of a boy being born for every birth. Well, we're talking about two different births. So the probability of the first one happening first is 51 over 100. This is 49 over 100. So you multiply 51 over 100 times 49 over 100, and you get just about 0.26. The last thing I want to talk about for the test too is the law of large numbers. We have the two probabilities. You have theoretical probability and empirical probability. The more simulation, the bigger the simulation that you're running to test your empirical probability, the closer you should get to your theoretical probability. It's like the theoretical probability of flipping a coin and getting a head is 1 out of 2. If you run a simulation and do it once, and you flip it and get a head, well, now your empirical probability is 1 out of 1, it's 100%. If you do it 3 times, you might get 2 heads, well, now it's 2/3, so it's still better than 1/2. But the more examples you run, the closer you're going to get to that probability, the theoretical probability of 50%. And the law of large numbers always talks about being on or over an infinitely many attempt simulation. So once you start kind of putting numbers on it, it kind of eliminates infinity. But the more examples you run, if we flipped a coin 1,000,000 times, we're going to be pretty close to that. We should be pretty close to that 50-50. It may not be exact, but you should be pretty close to that 50-50 theoretical probability. If you roll a dice 1,000,000 times, you should be pretty close to getting every single number 16% of the time. That's what 1/6 works out to be. So 1/6 of the time, you should get a 1. 1/6 of the time, you should get a 2. So we roll the dice 6,000,000 times, we should have 1,000,000 ones, 1,000,000 twos, 1,000,000 threes. The more you do, the closer you're going to get to that. But again, it may not be perfect because there's always randomness involved. Like we said, it doesn't mean things are due after a long sequence. You may be flipping a coin 100 times and get 10 heads in a row. That doesn't mean that tails is due. It's going to have to come out next because it's still a 50-50 proposition of getting ahead when you're doing the flip. But over the 100, you should be somewhat close to or closer to 50-50 than 75-25, something like that. Does that make sense? Okay, so like I said, that's the review of the kind of notes and everything you really need to know for this test. Kind of think back to some of the events we were doing, the games and stuff that we played, what you were seeing as you were doing that stuff, and then we will have the review packet. I'll put it out there tomorrow to kind of start working on that, and then I'll put a notice out at some point to figure out when I think we're going to be able to do the test. Whether I'm going to do, if I'm definitely doing a written part, where you have to figure stuff out and write things down, there'll definitely be a test for you guys on Friday in school. But with the weather being the situation as it is, I'm probably leaning more toward doing everything online on Monday so that everybody kind of takes it on the same day. It's all done online. It's going to be fairly easy for me to kind of to grade as well because there's only certain numbers you can actually have. I'll have to figure out a way to do it, but there are only certain answers you can get, so I might have to do the grading relatively easily and quickly on that. But that's a decision I have to make, and I will definitely let you guys know either tomorrow or Thursday, one way or the other. So have a good night. Talk to you later.